Hello, viewers. Today, I have the great privilege to introduce David to you guys. I am Anupam Vipul from Ahiravata, Chief Visionary Officer. David, can you please introduce yourself to our audience?
Yes, I'm David Haley uh, in the United States, and I'm a professional engineer.
Okay. So, could you describe how you got into this CV engine deal?
Well, it was a pretty long road. I guess, first of all, I've known Ron's father since about 1968 when I first met him. In fact, Ron was still in school,
Mhm.
high school at that time. And we've had a long relationship over the years. Uh, Ron's father's always been had a machine shop and big or little, depending on the businesses. And I also went into machinery manufacturing at the same time in Ron's hometown. And so I was over there in the shop a lot and in and out. And uh, Ron's father, Carl, was a very good mentor for me. He's pretty well shaped uh, that my look at technology. And I was just thinking, we go way back. We used to play a game called "Can You Invent This?" And Ron's dad, Carl, would state a problem, and then we'd see who came up with an answer first. It was interesting,
Okay.
and then I had my work took me out of the area. We sold the business and that I was in, and uh, pretty much traveled around the country from there, but always in engineering. I've never left engineering.
Okay,
Um,
so you are talking about 1968. So I think you must have remembered moon landing vividly.
the
Apollo,
1950s.
no, no, the lunar landing, Apollo mission.
Oh, yes, yes, I do.
Uh,
I do.
yeah, it's
Uh,
kind of a rare moment to meet someone who actually witnessed it firsthand. I think you were quite aware at that time. It's not just like you were a baby.
I watched it on TV.
Yeah.
Yes,
So
yes.
can you recall how big of a event that was in real time, basically, when it actually happened?
The amount of work from my work in engineering on much simpler projects, it was an amazing amount of technology and the coordination of it. It wasn't just knowing what to do. It was everything happening at the right time, the right place, uh, and and no more than you wanted. So it was marvelous. Uh,
And I think it actually helped everybody who was touched by this experience to really look into engineering. And there was an aura of mystery where it was like anything is possible. Did you felt that like anything is now possible? We have the technology, so to say.
Yeah, I'm one of the weird ones, I guess. I always, even from high school, intended to be an engineer. It was always what I was going to do.
Uh-huh.
And I caught a little grief for that because I wasn't exactly the highest in my class,
Uh-huh.
but uh, that didn't matter. I did it anyway.
Mhm.
And it's incredible what has unfolded. Just the math that I've taken. I still uh, take refresher or some uh, refresher courses in math or new math. I started finite element, uh, but I guess it's longer ago than I thought. But uh, that was that was I got a little bit of that in at University of Florida, but I really got into it in later years when they developed the software that would actually go on desktops. You didn't need a mainframe computer to do it. It put an incredible machine in the engineer's hands, and uh, things like that. I try to stay up on that technology.
So what
Uh,
was like a big technology change that you witnessed as you were coming up to the ranks?
well, the biggest for me was finite element. For the first time, you could actually manipulate and calculate a statically indeterminate structural uh, problem.
Okay.
And that was just, I've been waiting for that for a long time. Indeterminate structures has always been a very big problem. Well, that doesn't exist anymore.
Okay.
We can calculate. If you can draw it, we can calculate
And
it,
what
basically.
about the precision of the outcomes? Like how precise they are?
Oh, well, that's a little bit of a problem because that offers a greater precision than you generally need. And that gets people to do a lot more than they really need to. You don't need 6 decimal places,
Yeah.
not in the work that I do.
Okay. Okay. So talk about a little bit of your early career, like once you got out of the
Um,
university.
I'm sorry, what area?
Early careers, like once you completed your studies, what did you do after that?
Oh, I went into industry.
Hmm.
Uh, a lot of times, startups. I worked for a lot of established industry like Eastman Kodak, Monsanto, Becton Dickinson, Tropicana,
Hmm.
um, probably some more I'm not thinking of right now. But and then a lot of startups. One called Triangle Manufacturing, which we eventually sold to Campbell Soup. It was a sporting goods products, and they thought they would go from soup to sporting goods. I don't think that worked very well,
Okay.
but that's beside the point. We developed the company, the product, the process. Well, I designed the process to
Mhm.
make the product from scratch. It was a totally uh, unique to the product. Um, and basically, I've always been in R&D, even with all those companies. I'm not a manufacturing engineer. I'm the one you hire when you're not sure what you want to do.
Okay.
That's what I do.
So which year you started to interact with Ron regarding this constant velocity engine?
Uh, the best I remember, Ron's dad posed this as a project, and it was part of the "Can you invent this?" scenarios we went through. Uh, it we never got there for many. This has been many years, and Ron finally got enough time to sit down, and I have a suspicion it was all he was working on, and he came through. And Norm Stepnow, who's a good friend for many years, uh, uh, proceeded with the patent work for him, and uh, probably about a year 2011, somewhere, yeah, about there. Uh, we were close enough to the patent that it looked like time to make some entity to do something with it.
Mhm.
And that's when I stepped in and developed the company CV Global and, and raised the capital for that. Um, one person who came into the picture about that time was John Wallace. John died a few years ago, but he was the most incredible marketer and salesman I ever knew, and that helped us get the capital to actually get the prototype and uh, make 3D tangible products, and just kept improving from there.
Okay. So do you remember the first AA01 engine running?
Oh yes, I do. Uh, I was given directions from my wife to go out to Washington and don't come back until you have a running engine. And, that's what that's what I let Ron know. He asked me, well, when are you going home? And I said, well, when the engine runs.
Okay.
And so we worked on it from there, and and it was basically conversion from actually a non-engine, but uh, didn't matter. It had the motion, and went from there, and uh, had some hiccups with it, but it did run, and then we moved on from there.
And did you try to sell this quote unquote technology to any large OEMs?
So many I probably can't count them. The rejections became normal. Uh, I realized very early that big industry was we were disruptive, and we still are. We're going to be very disruptive, and I'll predict it'll be even more disruptive. Disruptive, not destructive. Uh, and uh, they and I told Ron this a while back, quite a while back too. We had to be a threat, or they'd never buy in. They've got to realize that, like it or not, they're going to have to accept this technology. So um, that's we keep striving more toward that, and I think that's getting close too.
Yeah.
But
So do you recall when you started to work with Naveen?
oh yes, that was, to me, that was the turning point.
So which year? Do you recall the year?
Oh, the year. Gosh, that's only been 2 or 3 years, I think.
Okay.
It hasn't been very long. It's moving remarkably well.
So now, do you feel confident that we were finally reaching the market?
I think we will.
Yeah.
We're past the tipping point. We have to. We got to go now.
Yeah, yeah, that's what I'm hoping for. Now, I would like you to dive deeper into this technology as it is, like, and talk about some engines that you are working on right now.
Oh
Yeah.
well, the engine I'm working on now is still uses and must use the CV technology. It's all based on a linear piston, um, and and a lot of features that brings to the table that just never existed before, but do now. And that basically, what I'm basically working on is the fueling and the uh, timing, and how it works from a fluid concept. The mechanical principle is done. It works,
Okay.
and I'm very excited about it. It's um, I guess I'm never quite sure where we are in confidentiality, but it's a two-stroke, and I call it the axial flow CV engine.
Can you expand on the reason why you are calling it axial flow?
Okay, any engine today, uh, crankshaft, and even the CV in its initial concept, uh, brings in fuel, compresses air, or compresses air, brings in fuel, and you have all this sloshing back and forth in the process. I call this the axial flow because it starts at one end and goes out the other. It doesn't reverse, and then that's you can't get much more efficient with your uh, fuel mixture and your airflow
So
than that.
almost like a jet engine.
Right, except we have a piston that goes back and forth.
Yeah.
The closest thing would be, well, a jet engine. Well, they've given way to turbines, but it's a turbine jet. That you have continuous motion with the turbine, but the fuel efficiencies, turbine will never approach what we can do with the engine.
Okay, now
I mean,
expand on this reason, the fuel efficiency part. I'm really curious about this.
well, okay. The fuel efficiency is not only the flow and mixing and continuous flow in one continuous direction, whether it's being compressed or ignited. That's part of it. The other part of it, it allows us to use features that the CV engine has created that you can never do with a crankshaft engine. And one of those, the most important to me, is constant volume combustion. That's where when the piston's at the top end, it sits there, and the ignition goes off, and you get whatever you want, uh, complete ignition or partial, and before the piston starts moving back in its recharge to its recharge position. So, uh, as a matter of fact, Department of Energy's worked with that. Dr. Peter Van Blaren, I believe. I hope I got that right. I haven't read it in quite a while. For years, has worked on constant volume combustion, but they've only been able to do it in single ignitions. They haven't been able to do it continuously.
Okay, now talk expand this part. You are so focused on this constant volume and combustion. Expand this part for so layperson can understand it. Why it is different from normal combustion engine like four
Oh,
stroke.
constant volume combustion.
Yes, yes.
Uh,
Dive deep into this part.
oh, that's a hard one to dive deep into. I think, in its simplest terms, it's not really combustion; it's ignition.
So
And
almost like a detonation. Are we talking about
it,
almost?
it almost not an explosion. Yes, it's a very fast conversion of a air fuel mixture to gas expansion.
Okay.
Uh, it, 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 it'd be, well, it'd be like diesel, except that it's a constant volume. In other words, when it goes off, it can't go anywhere except react, and that develops very high pressures.
Okay, because I have heard other companies also they are trying to achieve this sort of constant fuel combustion where they are like for emission standard, and they are always trying, but they are not actually hitting this target. So CV mechanism itself allows us to hit this target. Now you have talked about.
They know from Van Vlerengen's work that uh, emissions can virtually be combustion emissions eliminated, except for, I mean, you're still burning, so you're going to get carbon.
Hmm.
But uh, it they say, and this is theoretical, you should be able to get about up to 85% thermal efficiency. Now that's
85%.
yeah, if you're uh, with the constant volume combustion. Now
Okay.
you're going to be less than that because immediately you've now got to use it, and the
Uh-huh.
whole cycle is how you get your thermal efficiency. You don't get it just in this one little place
Uh-huh.
where you're very efficient. Um, and I'm not sure they may have thrown that into the calculations. That's not an area I got really interested in yet. We've got to be able to do it continuously first.
Uh-huh. So this constant velocity motion that we are achieving because of the rack rod, does that help into that actual combustion efficiency itself?
Oh, yes. The steady state in any chemical process is always good.
Mhm.
Uh, you uh, well, there's more to the linear than just the fueling. First thing you do is you eliminate friction from the sidewalls.
Uh-huh.
That, that gains you 10, 20% right there.
Hmm.
Uh, uh, the CV engine holds piston on the axis set in motion. The only thing touching the sidewalls is the rings, and that's not much
Mm-hmm.
in terms of friction.
Mm-hmm.
And all the other supporting elements are roller bearings. So you've got a ball bearing supported structure that's not touching anything. That's pretty low friction,
Mm-hmm.
not zero.
Yeah, of
But
course. But so basically, we are achieving efficiency by piling up a lot of small events, basically removing friction, removing side strikes, and having that constant expansion and better fuel air combustion itself. So all of these events are piling up, so we can achieve very high efficiency. Would that be fair to say?
exactly, they all contribute to each other.
Mhm. So we are at liberty of talking about this, so you can divulge as much detail as you want. And if the detail is not supposed to be out, we're gonna censor it. So do not worry about it. Uh, Talk more about like why you want to go to two-stroke. So.
Uh, well, two strokes in terms of internal combustion, you just can't do better.
Mhm.
Uh, as soon as you go to a four stroke, you just gave up half your uh, power.
Mhm.
A two stroke, and I think the public has been out. The negative on two strokes has been
Mhm.
pollution and uh, uh, and then smaller differences in how they're fueled and all. But we take care of the pollution problem because you do not need oil in the fuel
Mhm.
in this two stroke.
Mhm.
You um, uh, you just don't need it. So that got rid of all of those pollution components, the particulates.
Mhm.
Uh, 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 that's gone. And then we do it the combustion process we develop. That gets rid of your nitrous, your oxide, NOx, nitrous, the nitrides. They don't develop. I guess we should be careful and when we say we're eliminating pollution, well, what kind of pollution and which pollution? We're talking oil particulates, carbon particulates, and NOx.
NOx is
Some
a very core component of pollution. If we can reduce NOx, far more people would be willing to accept this engine. If NOx is very notorious, it's one of those very notorious pollutant to deal with. Even with a catalytic converter, it's a very nasty stuff. So if we can help ourselves in order to not produce it in the first place, that would be very optimum. That would be very
well,
optimum.
yeah, constant volume combustion is known to reduce NOx to near negligible.
Mhm.
I mean, you can do it. That's what we need to try.
Yeah. Okay. So, and talk about the power density aspect that we are achieving with this constant velocity design.
Oh, well, that's very good because we immediately, uh, and we can do better, but we can be at least half the size uh, of an equivalent engine,
Mhm.
a competitive or an exemplar engine.
Mhm.
Uh, so half the size is half the weight. Half the weight is less infrastructure. That's a lighter vehicle. You're carrying less from A to B,
Mhm.
um, and doing it with less fuel. So um, that's what the whole game is. And really, and we haven't stressed this very much. This is a much simpler build engine to build. I mean, this. Uh, I've been watching the latest advertising, and there's some pretty delicate looking machines out there that
Oh,
uh,
trust me.
and that's not necessary. This is
Yeah.
this is rock simple.
Yes.
It's that, and that's what I love about it is simplicity.
Yeah.
Right? This is not complicated.
We have an old saying: complexity is the enemy of reliability. So,
Well, a friend of mine used to say, "Any damn fool can complicate something. It takes
yeah.
a true genius to simplify."
Yeah. So Yeah, I'm at liberty of sharing this information that we recently had a conversation with interested party, let's just call it that, and he was curious about the costing, basically how much is gonna cost, and I said it's gonna be more or less the same, and little bit less, and he was like, how can you be sure that because we have so many different things? I said anything outside the crankcase is exactly everything else. It's normal cylinders, normal piston rings, timing valves, everything is same. We have been refining these things for a century almost, and the only thing that we are changing, they are not under as much stress as in other design. Fundamentally, basically the rack rod is not traveling at super high speed. Our rpm is not very high, like 7,000 rpm or even 15,000 rpm. The keeping rpm low also reduces so much basically extra friction that we have to deal with in terms of bearings, and the fact that almost everything is oil lubricated, and so fundamentally speaking, we do have a certain advantage in terms of simplicity. So I think your desire for simplicity has been met. So
Yeah, yeah. High RPM is the enemy of fuel efficiency, and it's always high wear.
yeah.
You just it, and it's high RPM has come about by chasing horsepower.
Mhm,
I don't even like to think of horsepower. I like to work with torque.
mhm.
That's what's doing the work,
Yeah.
and your maximum torque falls off well before you I used to say you spin a pencil fast enough, you can get 500 horsepower.
Yeah. I
It's
think
all based on speed.
Yeah, I think your statement has been taken true by Elon Musk, because his motor, the way he achieved such a high power density, the RPM is
Mhm.
so high that there is no bearing manufacturer that certifies the bearing for 20,000 plus RPM. So they had to like
Mhm.
basically remove the sealing in the bearings and basically squirt oil into it to make sure that it's cooled. It's almost like a jet engine bearing in a car, because again, as you said,
Mhm.
like if you spin it fast enough, you're gonna get have 500 horsepower, and that motor is like 20,000 rpm. So it's
Yeah, and unfortunately, uh, the efficiency for electrical production, the
Mhm,
higher RPM, the more efficient it is.
mhm.
It's the opposite of mechanical devices.
Yeah, it's almost so, but thankfully we have the technology of hybridization, so we can have a best of both world. uh, so that's what I'm very excited about. So,
Well, I can see us coupling to axial flux motors.
mhm.
Uh, yeah, motor. We can always gear up. I mean, if you really want something that you got to spin fast, like a motor generator, uh, then uh, use the torque and gear it up. Don't
No,
try to get
no, I don't think we need that, because there is another
no.
variable. Because let's just assume the motor, we require high frequency. So the motor generator unit electronics, they work at, let's say,
Mhm.
400 hertz. Again, the basic ones, some could go higher. We can just increase the pole count, so that way we can compensate
Oh,
for.
oh,
Yeah,
yeah.
that would be
You
much
know,
more simpler.
there's a lot better ways to get
Yeah,
electricity efficient than
yeah.
kicking frequency
Yeah. As
over.
in, like, that's one variable. We have lot of variables to control. That's just one variable. People like to have very high frequency nowadays. So we are like, okay, we can increase the pole count. So even at lower RPM, lower mechanical RPM, we can reach the higher frequency. Again,
Well,
that we can fine tune till chicken comes home. But that's the whole point. We have a
well,
lot of.
if we take a worldview,
Mm,
how many devices have to run that fast and that speed? Not many.
yeah,
Uh, I mean, our bread and butter is everyday transportation.
yeah,
Three-wheel bicycles, two-wheel bicycles.
yeah.
It's uh, I mean, and small cars. I believe that as an economy goes, we're working our way toward just enough. I this excessive horsepower and uh, my car's faster than yours. That there's no bread and butter in that.
Yeah, definitely, definitely.
Yeah,
Because to give some context, the road car vehicle barely wheel itself barely goes to like 2000 RPM in most day-to-day operation. So
that's a sweet spot.
yeah,
3,500. I mean, I can't see
yeah,
any. Well, there may be, but I don't see many applications for anything faster than that
yeah. You
because
can do Bugatti Veyron if you want to
yeah,
drive drive
yeah,
stupid fast.
you're talking just a few gears
Uh,
if you stay in the 3,500 range. Yeah,
yeah.
it's uh,
I think gear reduction will also help us a lot if we want to direct drive it. Because again, some of the cars now have six, some have 10 with automatic transmission. So reducing gear
oh,
count would be really helpful for us.
for small vehicles, there's a good chance you don't even need a transmission.
Are you sure
Uh,
about that?
I I'll say it's possible.
Okay.
We got at idling, we've got a lot of torque at
Okay.
what you consider idle in a crankshaft engine.
Okay.
Uh, it's if it's not a heavy vehicle, you may just need to let the clutch out.
Ah, so we may be able to just put a torque converter, that liquid torque converter, and that should allow us to even remove the clutch itself also.
Yeah, there are a lot of clutches that will are variable.
Uh-huh.
Hydraulic, uh, the same thing we're using
Uh,
in automatic transmissions.
uh-huh.
That may be enough to take off, and then you get up to speed and it locks. Uh,
That would be interesting to actually have a vehicle that without a gearbox, because again, that would be that right now is the biggest advantage with electric machines is that they are single direct drive, speed transmission. So that would be
well,
magnificent.
and you even have centrifugal clutches. You know, you don't. There's a lot of things to play with. The but and this is me talking because what I see, I think we need to start focusing on torque because
Mhm.
that's what we got, and start using that for your design, and forget horsepower. That's a waste of time
Yeah, definitely.
and fuel.
Yeah. So talk about what are you seeing in terms of fuel efficiency?
Uh, that's very hard to say, except it's going to be very good.
Hmm.
Uh, Definitive numbers, we've just really got to get in the lab because there's so many variables.
Definitely.
It's uh, and that's one of the things I'm looking at with the axial flow CV engine and the single valve. I'm really looking at a multi-fuel engine that adjusts on the fly. What can you buy? Oh, I can get gasoline. Okay. Well, I can't get anything but diesel. Okay. Alcohol? Go ahead. Hydrogen? Whatever.
Wait a minute. Wait a
Methanol?
minute. If you switch fuel, what are you doing in order to combat the basically knocking event? Basically, if you go,
Ah,
yeah.
your valve automatically adjusts, changes the compression, changes the timing. The
Oh, okay, okay,
timing's
okay,
with the valve.
okay, okay, okay.
One single little component does the whole thing.
Oh, okay. So,
And technology that's available too now.
uh-huh.
That wasn't available a few years ago.
So talk about
The,
this electronic valve and how does it help us to improve basically the whole system?
well, if you have an electronically controlled valve,
Hmm.
that means you not only have a profile established for whatever your engine is.
Hmm.
If it changes,
Hmm.
the engine doesn't run good, the valve electronically senses that and finds a point that it runs good. So what we will then have is a variable compression, flexible fuel engine.
Wow. So basically, we are this close to achieving Holy Grail engine.
I think so. Uh, it, it it occupies a lot of my thought.
Because just to provide a bit of side tangent, I have looked into a motorcycle, and US Army and almost all armies wanted a diesel powered motorcycle because they did not wanted to deal with logistics of multiple fuel. They wanted to, like, okay, our trucks consume this fuel, our tank consume this fuel, use that fuel into motorbike itself. They commissioned a lot of motorbikes from a lot of manufacturers, but none of them were good enough. And if what you are saying is even 70% true, we could be the one that breaks that barrier, where we can have actually useful diesel motorbike. That could be
Mhm.
very significant. I'm like, in terms of customer wise, that would be a sweet deal to finally break that barrier, where it's like, okay, you have one fuel that just, like, works in your tanks, works in your, all heavy vehicles are already tailored for that. It's the light vehicle that are the problem. And again, we are also working with drone engine manufacturing. So if drones can, instead of requiring let's say kerosene variant fuels or JP1, if it can directly run on let's say diesel, that's like shut up, take money. That's like flat
Mhm.
out shut up, take money. So I think you are onto something. Yeah.
Yeah. Well, there is something else on motorcycles. I rode motorcycles
Hmm.
ever since I was 12.
Hmm.
Uh, our engine's smaller and lighter. You've got to consider gyroscopic problems on a
Okay.
motorcycle.
Uh-huh.
Who was it? I think Sun made a motorcycle years ago with a drive shaft. It was pretty tricky getting that thing to turn a corner. It didn't want it wanted to go straight.
Oh, the shaft
Uh,
was spinning so fast that it created its own
yeah,
precession, I think.
it affected the ride. They didn't
Uh,
last too long with that. But our engine with its low mass is not going to have that big a problem.
uh-huh.
So you can have, and we don't have the speed.
Uh,
We're not running we don't develop gyroscopic torque
uh-huh.
just because it's small, and it's also linear. It's going back and forth.
Uh-huh. So there is a possibility that we could finally crack the diesel two-wheeler. It lot of
Oh, I
people.
think we.
Uh,
Oh, that would be my main target. Uh,
um,
uh, uh, I really see get we got to get rid of uh, the filthiness of a tooth, especially when it gets old.
mm,
Uh, uh, it's I think that's will be very good. And it'll even be good all the way up to a ship because we will be getting our torque with a much lower mass.
mhm.
So that big old engine, uh, the smaller that engine gets and gives you the same power, that's a win-win.
Definitely, definitely. Because I just wanted to remind you, I and Ron have a bet. So if once we actually test the engine, which we should be done quite soon, if the BSFC, brake specific fuel consumption, reaches
Mhm.
around basically 100, drinks are on me for whole team. And if it reaches below 100, drinks are on Ron. So where would you like to put your money?
Uh,
Yeah.
uh,
So,
I'll be honest with you. I've been so focused on the mechanics, I haven't calculated brake specific component
uh,
fuel consumption yet. Yeah,
uh,
uh, I better stay on the side and watch that one.
no, no, you have to take a, again, we are
Oh,
taking a leap of faith. We are taking a leap of faith here.
I'm going to take the low one,
Below 100,
under 100.
100 grams per kilowatt. That's what BSFC is. Basically, right now, the world record is 150 grams per.
Okay, I think we'll beat it.
Okay. Because again, to give some context, 200 is a very good fine-tuned four-stroke engine that, let's say, Toyota makes, and like a very
Ah,
fine-tuned. That is 200 four-stroke petrol engine. You have to go to two-stroke diesel to reach as low as 150. Um, you can do
oh yeah,
one.
Oh, well, as long as we keep the two-stroke in there, I'll take under 100.
Yeah, again, see, two-stroke, while it may not be popular in civilian use, it is the backbone of a whole shipping industry. So,
Well, we go directly to the heart of what makes it unpopular.
mhm,
I mean, it's uh, as soon as, yeah, and I remember service cycles.
uh-huh,
That was a two-stroke lightweight motorcycle in the U.S.
uh-huh.
for years. Uh, they would smoke and sputter and puff, but they keep running.
Yeah. So, what do you think about resiliency of our engine in terms of basically?
Uh, the resiliency is going to be very good because we have so many fewer parts
Mhm,
and that touch.
mhm,
Uh, and what does touch runs on bearings.
mhm,
Uh, the biggest wear will probably be in our reversing cam and the gear transfer. Uh, Basically, we got a pinion and a rack
mhm,
is is what the way we work.
mhm,
So that will be. Other than that, there's nothing else moving
mhm. So
except,
overall,
well, of course, the valve. But valves, that technology is very advanced.
yeah, it's a rock solid. It's been tested. It has been refined. So I think it's
Yeah.
uh,
And there, valves, there's even exotic fuels we don't even use, metals
yeah.
that we don't even use.
Mhm.
Uh, and I mean that's space age stuff. We don't need to get into that. Uh, of course, the longer this engine runs, eventually it's got to find a weak point, but um, it'll be in the reversing motion. That's but then that's easily repairable. I mean, you just slap the side plates off and put new rollers on and keep going.
Yeah, that's the whole point. Because again, you cannot make an engine that never requires maintenance. You just want to make sure that
No,
intervals
no.
is far enough. Interval, if
The electronics is probably going to be where we try to improve the longevity.
Mhm.
That even in new cars, I'm I just bought a new Chevy Traverse, and I can't believe how many things are controlled. I don't have any control over,
Yeah.
and it's that's going to be the first thing that goes wrong is that computer quits working.
Yeah, yeah. The right now we are very close to drive-by-wire, and people are almost this close to adding steering that is also drive-by-wire. So I'm like,
I'll be the last one that lets go of the steering wheel.
yeah. Lexus has already released one. I'm not even joking. There is like one or two cars that have that.
Well, I know they're going to do it, just like they're going to do AI, whether we like it or not. But
Yeah,
I don't have to buy in.
yeah. Yeah, so at some point, it's like our vehicle basically we went the. I think the sad part is we might have crossed the golden era where our vehicles were like, you buy once and you forget. Like you buy your car in like 1980s, you just kept repairing it, kept using it. Nowadays, it's like you have to replace your car because again, fundamentally, it will not last like a generation as it used to be. So and
Oh, the best thing that ever happened to America was the Toyota. Uh, Suddenly, cars didn't wear out at 60,000 miles, and I remember when 50 or 60 was it. You had to start looking at that. I do go way back.
uh-huh.
My first car was older than I was, 34 Dodge, but
1934 Dodge.
34,
1934.
1934. Yeah, that that car was older than I was.
Damn.
Not much, but it was.
Yeah.
And uh, it, but even into the 50s, 50, 60,000 miles, and you start looking for another car.
Uh-huh.
Uh, that went as soon as Honda and Toyota uh, showed what you could do when you start doing quality.
Uh-huh.
Uh,
So, what
It,
do you think was the reason for this disparity between American automaker and Japanese automaker? That this disparity was, like you know,
oh, I know exactly attitude.
ah,
They 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 have a wonderful culture when it comes to product development. What you make and sell to the public,
hmm
um, and quite frankly, that took a while to catch on in this country.
hmm
And
so
but but they they just I mean, and everyone in the company is involved in watching the quality of this product.
yeah,
That's hard to beat.
yeah. So, in terms of our CV engine, do you think we can meet military standards for engine reliability?
Military standards might be a problem because there are no standards for what we have.
Yeah.
But we can handle that. I talked to the Marine Corps at great lengths, and at the time, uh, they were very interested, but they had already spent their budget,
Oh, okay.
and it was at that time when there were not going to be any increases in the budget, so it wasn't going to happen for years.
Uh-huh.
But they were very anxious to. Matter of fact, he told me a project that they had put their money in. He wished he could get it back and put it in our engine. But that doesn't happen. You don't reverse flows.
Yeah, yeah. But I think once Ahiravata has finally started to make engines, you can maybe just bring one piece to them and see whether they like it or not. Because,
Yeah, it's got the reliability and uh, and uh, and performs meets. It'll have to meet specs,
hmm
and that's going to be easy because we can outperform any specs they have.
hmm
I mean, that's easy.
hmm
Uh, uh, that'll get their attention real fast.
hmm
One of the examples would be on more and more power is used by the field forces, and you have to carry your generator with you.
hmm
Well, if you grabbed an American or any generator at this time, you, there's going to be two of you.
hmm
We can get this down so that you can very easily backpack a field generator for this.
how many
Uh,
kilowatts we are talking about?
um, I'm well. It only takes about 20 to 27 to run a car,
Uh-huh.
so we're probably talking 5 kilowatts.
Okay. So, okay, yeah.
And but if it's uh, field electronics don't require a lot of power. They just require it all the time.
hmm
Uh, I mean, you can't carry enough batteries to
Yeah, yeah, yeah.
an output. So, but you can carry fuel,
Yeah.
or you can find fuel.
hmm
And I think that's another advantage we'll have as well. You can't find gasoline. Well, switch it over to diesel. No problem. It's built into the electronics. All you do is change the valve timing.
hmm So, are you envisioning that we have an engine, we pour fuel in, and if the fuel mix change, basically, let's say you have gasoline going through and we directly pour diesel, there will be a bit of mixing and then there will be stratification based on the density. So, engine,
I'm not sure, particularly in the diesel to gasoline scenario. I don't think we can do that because the uh, if you've ever put gasoline in a diesel engine, you won't do that again.
uh,
You don't want that situation where you're running on diesel and and then somewhere you get a blend and then you make your change. That's too traumatic. A gasoline to diesel change will probably require you to drain out your diesel
mhm,
and shift to the gas. Uh, there are other fuels that are closer that you might could do that.
mhm.
Uh, like alcohol would blend very well. And
So you do expect a cleaning cycle, let's just put it that way. You do expect once you clean it out, then it should be easy thing to do.
oh yeah, just pour it in
Yeah, okay, okay.
and crank it up, and then It wouldn't take a few turns and all the systems adjust to what the new fuel is.
Hmm. Yeah, that would be a significant advantage to actually have that, where you can just rinse and change the fuel. That would be
Yeah,
a.
yeah, yeah. It's just electronic programming after that.
Mhm. Yeah, that.
Once you have that situation set up,
Okay.
I'm excited about it. I believe it'll work.
Yeah, yeah. So yeah, I also think. What do you think will happen to our engine if it's locked at synchronous speed? Let's say you are making a generator and it's meant for 1500 RPM. Synchronous, basically, the generator part is synchronous. It cannot switch in the RPM. So, would our engine perform in that sort of scenario where RPM cannot change? Because again, it's a synchronous system. So, how do you think our engine will perform? A lot of diesel power plants are synchronous generators, so you do need that. So, how do you say that will affect our engines?
Well, the generators, in order to meet the electronics
Mhm,
side, have to perform at a certain level.
mhm.
Uh, I don't know what you can do other than meet that level. So maybe I don't understand.
Okay, okay. Think in this way. It's an analog generation unit. Though no electronic control, is just a dumb analog generator that is converting the rotation into electricity, and its frequency, basically the 50 hertz in India and 60 hertz in USA, that is locked to the RPM. If you increase the RPM, the 50 hertz become 51 hertz, 52 hertz, 53 hertz, and if it stalls under load, it will go down to, let's say, lower hertz and lower hertz. So that's what I'm talking about, like in terms of synchronous generation.
Yeah, I'm not really versed on the generator side.
Okay,
That's not an area
okay,
that I've worked in.
okay, okay.
But my understanding is that's all electronic now, and they have limits. I mean, if you need 50 hertz, you need 50 hertz.
Yeah, definitely.
Uh,
That's why we use synchronous generator in every power plant. That's the whole point of it. So yeah,
yeah,
that.
I would, and I only this is only logic on my part. Uh, I would think you would not. I would not want a mechanical device trying to hold what you need for electronics, like 50, 60 cycle. The mechanical devices aren't that sensitive. they're
Yeah.
not going to do it.
Uh-huh.
So there's always an electronic. You'll be controlling the interface electronically always. I don't see that changing.
Hmm. That's unique take. What we have hollow shaft. Do you have any use case for that?
Oh goodness, yes. The first use is you can make a single engine pair, and you can put a center shaft in it and just start stacking them. So you can have a big old engine just by stacking them together and bolting them up tight.
So almost
Uh,
like a modular Lego engines, where you're just like, okay, I
yeah,
have.
yeah, and the other thing, this is a product that I've been working on. Imagine, uh, 179 cc. That's probably too big, but that with a with it hollow, now you take that engine, you put a shaft through it, you put a bicycle on the other end of the shaft,
Mhm.
you put the motor engine on this side's the clutch, the shaft's running through the bicycle wheel, and you're hooked up. You got your drivetrain.
Uh, okay. So it's a motorcycle that has like engine at.
My motorcycle the same.
Uh,
Scooter, you just you hang the engine on one side and the clutch on the other, and the axle goes all the way through.
uh-huh. Uh-huh. So, what's your thought on in terms of drone engines? Ron is working on one drone engine. So, what's are your thoughts on that?
Oh, the drone engine.
Yeah.
Uh, well, the neatest thing there is the aerodynamics. We're low profile, and and spread out. You don't have this big old front that against. So with that, and then we're the torque we have is a win-win. I mean, the engine's low profile. I think our engine will actually fit in the airfoil, in the profile airfoil of the wing, if it's a drone with a wing. Now, a lot of drones are more like helicopters with the
Quadcopters, yeah, quadcopters you're talking about.
quadcopters. Now, let's see, where would you? Well, that would still be horizontal because you take the shaft and you'd run it sideways. Uh, uh,
Oh, for quadcopters, people are generally running it by basically a generator on engine and then using electricity. So,
oh well, that's easy. We just take the CV engine and run a axial flux generator. Uh, well, that's real easy.
yeah,
You just put that one in the center.
yeah. People prefer that because that way they use it as a range extender. So if you're only doing
Yeah.
like short range flights, you just run on battery. And if you're like, okay, no,
Well,
I have to travel far, you use fuel.
we had the small size, the efficiency, and also the quietness comes with that too. You're not running a high-speed engine, which makes a lot of noise, distinctively makes a lot of noise. And I'm sure that's part of the tracking and detection technology too. Um, we'll be down at a low enough RPM that probably the only thing you hear is the props.
Yeah. So what do you think?
No, I think there's a due to the weight and the fuel efficiency, there's a big potential for drones.
Yeah. I was curious about how do you think altitude will affect it? Height, altitude.
Oh, altitude. Well, everybody's got that problem. There's only so much air up there, and that's what you need is oxygen. Um, I'll make a guess that if somebody wanted me to make a high altitude drone, I would start looking at the fuel and see if I couldn't do a fuel that would take everything it needed with it.
Like ethanol, kind of like alcohol, kind of.
No, I'm thinking more like hydrazine.
Dude, that becomes a rocket. At that point in time, you are dealing with rocket.
I don't think anybody at the military would even touch it.
Yeah, at that point,
But,
it's a rocket.
yeah, for any internal combustion engine, there's just going to be a limit to the altitude. There's not going to be enough oxygen.
Yeah, that's the core selling point of jet engine because of the forward motion and everything. Like they do survive better in that regard. So, so I think even if we have better efficiency than jet engine, I don't think we can replace them because of this weakness.
Yeah, you can't be all applications because especially when this engine comes out, there'll be a real divide between what you put this engine in and jet engines. I mean, it just this is not practical for high altitude flight because it's an internal combustion engine. It's going to have the fuel in the air ratio, or it's not going to work. So yeah, we're not going to push jets out of the picture.
No, but jet engines are being pulled downwards, if that would be a correct way of saying it, where basically they are used in drones right now because of the power to weight ratio. And if we can meet the power to weight ratio, not high altitude, power to weight ratio for low altitude crafts, we should.
Well, there'll be a limit in the drones at the very, very little ones. I mean, well, you can look at your model airplane engines. I mean, they make them from very tiny. Well, also, I guess our engine is so precision for the interior motion
Mhm.
There's a limit to technology to even make. The littler it gets, the harder it gets to make.
Mhm.
So if you want to get real tiny, we'd have to put some thought in that, and it might turn out to be a throwaway engine. I mean, it's not going to run long, and emission engine, it's only got to run till it gets there.
Yeah. So, what's your thought on that AA001, that first engine you built? Can we make it reliable and long lasting?
Oh, the AAL1 can definitely be improved. Uh, that, but uh, as long as we stick with the two-stroke engine,
Mhm.
I can't see any reason not to make our axial flow engine. It just solves so many other problems, uh, it doesn't have to be adjustable. I mean, it can be a fixed engine.
Mhm.
It just uh, and that's just timing, and it's just timing. You could do it mechanically and have it set for a single fuel,
Mhm.
but
Okay, so
so
we.
it's not a showstopper. I mean, you can make it fixed. You don't have to take the flexibility. That's but you're going to have the electronics anyway, so you may as well use it.
Fair point. Okay, can you tell me something about Ron and your partnership as it basically the CV Global started to grow?
Oh gosh, it's been so many years. I guess we've been 50 years. Um, Ron, the only problem I have with Ron is he never quits designing. At some point, you got to take it away from him.
uh,
It's,
yeah,
it's perfection can never be attained, and
yeah.
pretty soon it's what a draftsman I used to have. He had a wonderful phrase: "Good enough." It's good enough, and so you take it off the drawing board and make it
Yeah,
and improve it,
yeah,
but make it.
yeah. At some point, you
Uh,
need to put the pencil down. At some point.
some some point, put the pencil down and let's see what it'll do.
Uh-huh.
And also in my years of research and development, we never worried about the first of anything. I
Mm-hmm.
mean, you just make it work, put it
Yeah.
together, anything. Balin wired, wasn't pretty, it didn't matter. Make it work, because then you start fixing the things that don't work well.
Mm-hmm.
That's easier than the first time.
Yeah, definitely. Because I don't think there is any better teacher than real world once you actually build it and test it. I don't.
Yeah, nothing like the real world.
So you can keep
You're
going in
right.
circle. Yeah. So,
Yeah.
and it's kind of shocking that Ahiravata as a company, we are just starting and we already built a cylinder, sorry, three-wheeler engine that we showed in our expo. And then we are working on that four-cylinder engine, 1 liter engine. And then we gonna work on a drone engine. And then you are working on a truck engine. So we have so many engines right now going on that it's.
Well, yeah, and you might want to be careful, because uh, something like this, suddenly it'll go anywhere you point it, and
Mhm.
and that's too much. I mean, that would stagger even General Motors.
Yeah.
Uh, you just you the best bet is to look at your market
Hmm.
and make what somebody needs.
Yeah.
It's, that's a lot better than trying to convince them they need something.
Yeah, let
Find
the money
one
flow.
that needs it anyway.
Yeah. So I think the best bet would be to let the money guide us. Basically, wherever the money is, we should just follow it. I think that would be a
Mhm.
very healthy decision. Okay, so it's been a very nice talk. Would you like to give any final remarks?
Oh well, I guess from my perspective, uh, I'm always driven to simplicity.
Mhm.
And so whatever the engine is at this point, I'll always be looking to try to make it more simple,
Mhm.
and I think it can. It's just, and this engine offers us opportunity for simplicity that are absolutely impossible with the crankshaft engine. You just can't. There's nothing to work on. This is wonderful. This has so many unexplored features, and every one of them will add to the other. It's just well, it's hard for me to even talk, and I suddenly start thinking of some of them, and it's just I think we're with Naveen, we've just arrived. He's got and is in the position to move this thing, and
Yeah,
that's what's been needed. Um,
definitely.
and I don't want to. That's why I've been reluctant to talk about the axial flow. I don't want to divert where we are because it's important. It'll be important to support the next step. And what I'm really working on is the next step, not the first step.
Yeah, we need to put the pencil down at some point. We need to put the pencil down.
You put the pencil down
Yeah,
somewhere,
yeah.
and uh, and it doesn't have to look pretty the first one.
Mhm.
Just
Definitely.
just quit polishing it.
Yeah,
Let's run it.
yeah. So this was a very nice talk with David, and I hope you guys have enjoyed it, liked it, and thanks for watching.
Yeah,
Bye.
well, I hate to ramble, but I do. So
Yeah. Such is
thank
life.
you.
Such is life. Such is life.
Oh yes, it's a lot of fun.
Yeah. Okay.